Welcome back to session 19 on plane stress and Mohr's circle. We're going to get going with our second portion, our second part here. In this part of the session, we're going to cover how we go about constructing Mohr's circle to be able to analyze the transformations of material elements. Okay? And this procedure will hopefully be pretty straightforward, but there are a number of steps. So the first step for making a Mohr circle is to draw the axes. And we discussed this briefly last time, but the axes are in the sigma direction. So this is our x, our horizontal axis, and in our tau direction, so going downward. Then you just had an example where you got to calculate out the center of the circle as being the average of whatever sigma x and y you might be given. So we go ahead and we calculate that out, and then we can plot it out as shown here. Okay, so this will become the center of Mohr's circle. Then we will go ahead and plot a reference point. Okay, so in the last question, we had the opportunity to calculate out a radius. And we're going to use that radius in just a second. It's going to be the next step. But what we typically do before even calculating out the radius is we just plop this point down. And what is this point? Well, let's say we have an element with a state of stress, and right now, you can plot sigma y as well, okay, and we'll get into that, where sigma y is, but just take the sigma x and the tau xy, right? So sigma x is going to be somewhere on this axis, and it's marked here, right? So this is sigma x, and then plot in the vertical direction downward tau xy. So remember, tau downward is positive. So this is tau xy, and it would be a positive quantity until we plot this point. Now, this point to the center has an interesting property, and this point is on the Mohr circle. So since it's on the Mohr circle, it corresponds, or its length, right, the length of CP here, corresponds to the radius, and we previously described how we can calculate out that radius. Okay. And something to note here, often if we have numbers, we're not looking at this formula. Okay, this formula is going to hold true. Okay, so of course many of us are just going to look at it. I'm included, often I will, but I don't need to. If I'm interested in calculating out the radius of this length CP, and I've already plotted my C and my P, and I know where C is at the average, and I know where sigma x, or I know where P is horizontally, right, sigma x, I can say that this length right here, okay, is going to be sigma x minus sigma average. Okay. And guess what? Sigma x minus sigma average is just this term, sigma x minus sigma y over 2. That's right. So does this come from that, or that come from this? Well, the math is what we use to derive it, but Mohr is giving us a nice graphical representation so that we can calculate out the radius without reciting this equation every time. And this length is just tau xy, right? So we can figure out this length and this length to be able to figure out the r. Okay, and so here you go. Sigma x minus sigma y is 2. And yeah, we can write out the radius, right? But we've already got it. We know it's right here. So at this point, we've now constructed Mohr's circle. using minimal amounts of math. Okay? And so that's kind of nice. That's kind of convenient. And now we also can put this angle in. And we still haven't described what that angle means. But we'll do that as we do some examples, okay, in a few minutes. Before we get into how to use this 2 theta, right, which theta does correspond to the rotation of a material element, so foreshadowing, okay, and there's a 2 there, but 2 times that. But before we do that, let's just talk a little bit about what we can do with Mohr's circle. So one thing that we can do is find stresses in an arbitrary orientation. Okay, when we're talking about that, or at least we're talking about rotating this material element. So we can rotate by 2 theta on Mohr's circle in the same direction as the orientation. Okay, so this rotation of 2 theta on Mohr's circle actually corresponds to rotating a material element just by theta. So if a material element rotates 45 degrees, then on Mohr's circle, it goes 90 degrees. If a material element rotates minus 5 degrees, then on Mohr's circle, it goes minus 10 degrees. Okay? So Mohr's circle is useful for figuring out a stress in an arbitrary orientation. Okay, so like this. So let's say that we're interested in going from our state of stress given here at P, and we're rotating counterclockwise. Okay, so this direction, counterclockwise, on the element, or the element's rotating that much. Then we go 2 times that amount on Mohr's circle to get to a new point, okay, that corresponds to a P prime or a sigma x prime and tau x prime y prime. And on the other side of the circle, now you're like, this is wild. We can figure out what sigma y prime is, right? Over here it's telling us what sigma x prime is. And we put this minus tau x prime y prime. Now, why is that? Well, remember what happens when we rotate an element 90 degrees? The y becomes x, right? And then x can become y, right? When we rotate 90 degrees. Look, 90 degrees, 2 times 90 degrees is 180 degrees. Now, this may not look like it, but this is supposed to be a straight line coming across here. This is supposed to be 180 degrees on the other side of Mohr's circle from P, or this point over here is 180 degrees from P prime. So there's, and similarly, there would be a P another on the other side, or we want to call it something else, but maybe we'll call it Q later. That's 180 degrees on Mohr's circle, which corresponds to the 90 degree transformation, right? Which corresponds to sigma y, okay, if it's from P. Okay, so this is giving us a little bit of insight in terms of how we can relate the rotation of the material element to Mohr's circle. And remember, if we go back to the equations and the transformations, there are 2 thetas in those equations. There's cosine 2 theta, there's a sine 2 theta. And so the material element, when we did the transformations before, we had to multiply, or we had to be careful about dividing by a factor of 2. And it still holds here with Mohr's circle. Now, arguably, what we just discussed with finding stresses in arbitrary orientation is something we can do with Mohr's circle, but it's not really, in my opinion. You're probably going to want to use the general equations for stress transformations in 2 dimensions, okay, for this type of kind of arbitrary rotation. Where Mohr's circle becomes very helpful and faster is when we look at finding principal stresses and finding maximum shear stress. So what in the world's going on here? It says, okay, look at the horizontal axes. Okay, that's fine. Okay. I'm looking at sigma. And then look at a rotation 2 theta p. What are they talking about? Here we go. Look at this. 2 theta p we can think of as the amount that we have to rotate this CP, right? And maybe it would have been CQ on the other side. It's not drawn. Okay, but to get to a state where the shear stress is 0, right? On this line, tau equals 0. So, and then also we see that we're going to the outskirts of the circle in the sigma direction on the horizontal axis. And we're going on this side too, right? We're going to a minimum. And our max and min in-plane principal stresses, okay, are being found this way. So this is pretty cool that we can figure out what the orientation is to get there, and then we can figure out what those quantities are just by using this circle without using much math. Now, the other thing we can do is we can try to find the maximum in-plane shear stress. And this has to do with getting us to a situation where the shear stress is a maximum. So it's going to be at these locations, and positive max is going to be at the bottom. And look, now let's say that this was rotated a negative amount from here. Well, it's not. The way we've drawn it is this 2 theta s is going this direction. So if this were sigma x, this would now be sigma x prime up here, and we'd have our tau x prime y prime up here as well, and we have a minus tau x prime y prime down here. But if we're interested in kind of the maximum shear stress, it doesn't matter whether it's negative or positive too much, okay? We just need that quantity. And this is symmetric because the center of the circle is always on the horizontal axis, all right? And we can again figure out how much we have to rotate 2 theta s this time to go from this state, okay, or this set of stresses to this one where we now have a maximum shear stress and we have the normal stresses being equal to each other and being equal to the average. All right. So let's now do some more examples. All right. It's a little bit hard sometimes to get this when we're first talking about it. There's a lot of things to remember. All right. But hopefully with the number of examples that we've packed into this session, it will not be too difficult to use Mohr's circle. So now we say, here's an element, 100 megapascal for sigma x, 50 megapascals for sigma y, tau xy is equal to 10 megapascals, and we rotate the element 30 degrees counterclockwise. What are the resulting sigma x prime, sigma y prime, and tau x prime, y prime? This is really what I consider to be the hardest thing to do in Mohr's circle, because we're not going just to the extremes this way or the extremes this way, right? The extremes this way give us principal stresses. Extreme this way give us the max shear stress. What we have to do is figure out where we are and then apply rotation. Okay, figure out what the configuration is and then apply rotation, transform. Okay, but let's go ahead with the process. We're going to draw the axes, tau going downward. We're going to plot the center of Mohr's circle. And, as we transform, right, even, if we go to whatever sigma x prime, sigma y prime, it's going to give us the same center, right? Mohr's circle is not going to be moving on stress horizontally. Then we plot our reference point, okay, like so. And right now we have 50, 10. All right, so 10 is the orange direction, and 50 is the green one, okay, and it's off from this average stress as well. Okay, it's to the right of it, which makes sense because it's larger than sigma y, right? And then we can figure out the length of this radius, okay, that we have here. We can do that. This is where it's often nice if you have the numbers, because you can just kind of do it without using any math. You're like, oh, okay, what's the length here? Well, that should be 25 because I'm at 50 here, and this is at the average. All right, or I'm sorry, we're at 75 here, and 50. This is wrong. Sorry, this should be 100. Okay, and then we figure out what this length is. It's going to be 25, and what's the length of this side of the triangle is just 10. So the radius is going to be the hypotenuse, and it comes out to be 27 megapascals. Now, if we want to get to a new destination or a new orientation with this rotation of a material element, okay, so the material element, I don't have a line here, but material element, right, that we're going to be rotating some amount, right? This is the horizontal, right? And this is angle theta. That's rotating 30 degrees. On Mohr circle, it's going to be rotating 60 degrees. So what we need to do is apply a rotation of 2 theta. So we do that, okay, and that will get us to a new location. Nonetheless, it's not super useful if we don't know what the slope or what the angle of this line is, the CP line, okay, originally. So it might be useful to define another parameter like a phi, or, if you want to be more careful, like a 2 phi. But it's not going to matter too much. It just gives us an opportunity to write out, okay, this is where I am. This is what the angle of that line is. And then we're going to go 2 theta. We're going to go 60 degrees around. And then we can get to our new point when we do that P prime. And when we're describing that P prime, maybe we want to know where P prime is, not so much for the sake of, for practical purposes. It doesn't, I mean, we know it's 2 theta. We know it's 60 degrees from this CP line, but it'd be nice to know, okay, it's an amount alpha or some, where is this, what's the angle with respect to this horizontal axis, so that we can calculate what sigma x prime and tau x prime, y prime might be, basically just through geometry. So here we get that this angle, okay, so this one was down at 21.8 by using the arctangent, or using the tangent, right? So this is 10, this was 25, right? We could figure out what this angle phi is, and we know we're rotating 60, and so we can figure out that alpha is going to be 38. It's going to be 60 minus 21.8 to get us this angle with a horizontal above the axis. We can then use this information, all right, with the radius, which we already have. So we have our sorry, not alpha, gamma. We have our gamma, and we have our radius. We can say that this quantity, so this horizontal quantity here, is going to be sigma x prime minus, okay, the average. That's this length, right? So from here to here, just like we did to calculate the 25 previously, that's the sigma x prime minus sigma average. So that's what we've written there, and we can calculate out now what sigma x prime is. And it's gone down a little bit. It was at 100, okay, and now it's gone down to 96 megapascals. Similarly, if we want the tau x prime y prime, right, so we want to know what this is, we can say, oh, well, r sine gamma, okay, is going to give us this height direction. And it's negative. It turns out it's negative because we're on the opposite side from where tau is going positive. Okay, so then now we can calculate out what tau x, excuse me, what tau x prime y prime is. And if we go all the way out to this q, all right, and we want to figure out what sigma y prime was originally, and what the new sigma y prime is, okay, down here, all right, we go down this direction and we can solve, okay, for the sigma y prime. What is sigma y prime? Well, it's going to be very similar to what we had here when we were figuring out sigma x prime, right? It's symmetric. It's the same distance horizontally away from the center. And so we can think of it as being, excuse me, the average, this distance, minus the r cosine of gamma. Okay, and so we get, that's 54 megapascals. So this is a little bit tedious. Okay, honestly, you're probably thinking I'll just go ahead and use the stress transformation equations, and I wouldn't hold you too much at fault for that, okay, for doing these types of transformations. But where this Mohr circle starts to become very interesting and fun and useful is when we start looking at principal stresses and max shear stress. Okay, so what you see here is the same thing we just had, including this error with the sigma x, okay, stress. And we've got the same configuration that we just had. We went through the first few steps. We figured out the radius. And now they're asking, or we're asking, or I'm asking, what are the principal stresses and relative orientation? Well, to get to the principal stresses, we just need to get to this horizontal line, okay? Because that's going to put us out. My circle is not super great, but it's going to get us out to the left and right sides, the limits, the outermost parts of the circle, at least relative to the sigma axis. And that's where our principal stresses are going to be. So what's cool here is you look to get from here to here, it's just adding sigma average plus whatever the radius is, and that will give you the higher principal stress, and sigma average minus r will give you the lower one. All right. To figure out the orientation, okay, how many degrees we have to go up. Well, it's nice that this is a triangle. Now we're just looking at, hey, what is this angle relative to the horizontal? So it's also simpler than saying, hey, go an arbitrary 30 degrees, and I have to know where I was, and then how much I'm going, and then where I am again to do these calculations. But here, we can just look at this 2 theta p as being, well, what's this opposite side is 10, and what's this length? Okay, that was 25, which we determined previously, right, from sigma x minus the sigma average. So we can solve, and we now know that on the material element, it's a rotation of 10.9 degrees. On Mohr's circle, it would be a rotation of 21.8. When we are at this location, we can say sigma 1, like kind of verbally said just a few minutes ago, is equal to the sigma average plus r. and that's what you get here. If we want to know what the smaller value is, okay, for principal stress on the opposite side, okay, going right along this line through the middle, okay, to the other side, it's going to be essentially the average, sigma average, minus the radius. Okay, so over here, sigma 2 is what we're interested in, because I said let's find them both principal stresses in this case. So that's going to be sigma average minus R, which is 53 megapascals. Okay, so we've gone ahead and we've figured out the relative orientation right here, and we figured out what sigma 1 and sigma 2 are. And as a note, usually when we're talking about principal stresses, we say sigma 1 is the larger of the two. Okay, so sigma 1 will be the larger one, sigma 2 will be the smaller one. And then if there's a sigma 3, that's smaller yet. Okay, and so we put them in that kind of highest to lowest order. Let's look at another example. Let's find the in-plane max shear stress. Okay, same numbers as we had before. So that means that this is supposed to be 100. Same initial steps, calculate the center, calculate the radius. But what do we need to do? Well, we need to get vertical. All right, we need to rotate this CP line so that, I guess I've said CP multiple times, but that's C is the center. Okay, so we're saying CP, rotate that line such that it gets vertical, and that will give us maximum shear stress. So in this case, I'm drawing 2 theta s. Now notice this is in the clockwise direction, so this is opposite of the direction we have been going for these previous couple of examples, and that means that the element is going to rotate in the opposite direction as well. Okay, it's going to go clockwise instead of counterclockwise. We're trying to get down to this location. We could call it Q, and this point up here we could call it Q prime, and we can write out that Q is the average plus it's the average for the X, and then it's simply the maximum shear stress, okay, because it's all the way at the bottom. And this is going to be the average, so that's the defining X coordinate, and then it's the minus tau max up here, okay? Now, what is tau max? Tau max is just the radius of Mohr's circle. So again, this is really nice. We can calculate pretty quickly what the maximum shear stress is by just calculating out what the radius of the circle is. Okay. So, did I not? I didn't write this. I had to fix this question though, because I wrote. What are the principal stresses and relative orientation? No, that's not what we were doing here. We are looking, oops, that actually is for this problem we are. Let's see, that's that. But this one is what I did wrong. Okay, this one is max shear stress. Okay. Okay, so we already kind of discussed this, but I just want to point out that if you rotate 90 degrees on Mohr's circle, okay, well, let's say this is actually a rotation of 90 degrees, okay, on our element rotation. So this is element rotation. Rotation of 90 degrees on Mohr's circle. What does that look like? Well, we started with our sigma x over here. If we rotate 90 degrees counterclockwise, we now have our sigma x prime and our sigma y prime over there. And our tau x prime y prime is over here too. So look, we went from having a positive tau xy to now having one that is negative. All right, if you essentially rotate this element backwards, look, the arrows are going away over here. They're going away from the tau x prime y prime, so it's negative. And then now the sigma x prime is what sigma y was, and this sigma y prime is what sigma x was. Okay. So how does that bear out on Mohr's circle? It should bear out pretty well. Okay. So we have our Mohr's circle and stress depicted at point P, sigma x, tau xy. And we are going to theta, or we're going to 2 times 90 degrees. Like we said before, that's 180 degrees. That puts us way out here. And look, now that stress, that shear stress, is defined by negative tau. Okay, so that makes sense. And this going all the way over here, this was already our sigma y, okay, out here. And our sigma y, comma, minus tau xy, and now it's sigma x prime, right? So again, that reinforces what we were saying here concerning what happens when you go 180 degrees on Mohr's circle, or 90 degrees on the rotation of element. So now there are some questions. There are actually a number of them, okay, to kind of give us some practice with rotation of material elements. Here we have sigma x equals 10, sigma y equals 50 megapascals, and tau xy equals minus 10 megapascals. Go ahead, use Mohr's circle to determine the larger in-plane principal stress. Okay, and you may not have these exact numbers, okay, but this is a chance to figure out what is the larger principal stress. Okay. The next question is, for the same element, what is the angle rotation required to get to the transform state of principal stresses? So we kind of did that previously. The next question is, if we have this element, how do we determine the max in-plane shear stress? All right, so we kind of did that example previously as well. So opportunity to kind of practice that. And then what is the angle required? Okay, the angle of rotation required that will get us to this transform state with max in-plane shear stress. All right, so those are the questions to be able to practice our skills just on the material elements at this point. And in the next part, we're going to talk about some structures that we've looked at in the past, state of stress, and what happens when you use Mohr's circle to figure out principal stresses or maximum shear stresses under those circumstances. Thank you.